Welcome to the class. Dear students, today we are going to see Reformatsky reaction. We will see in this video class, we will see which compound shows Reformatsky reaction, what is the product of Reformatsky reaction, what is the reaction in itself, and then we will see one or two points regarding the reaction, and then we will see the mechanism. There are three steps in the mechanism, we will see that, and finally we are going to see the significance of Reformatsky reaction. So let us start the video. Reformatsky reaction. So Reformatsky reaction is shown by carbonyl compounds. It is shown by carbonyl compounds. What are the carbonyl compounds? Aldehydes, ketones and esters. So it is shown by aldehydes, ketones and ester. This reaction is shown by aldehyde, ketone and ester. What happens in this reaction is a carbonyl compound is heated. It is heated with alpha halogenated ester. This is an ester, right? This is ethyl acetate. Ethyl acetate. It's an ester. This is alpha carbon atom to the carbonyl group. This is the carbonyl group, that is a functional group. This is the alpha carbon atom and this is alpha halogenated, correct? So it is alpha halogenated ester. This is ester, ethyl acetate, correct? This is alpha carbon atom, alpha halogenated ester. So what happens in this reaction is when a carbonyl compound is heated with alpha haloester or alpha halogenated ester in the presence of zinc in an inert solvent. Take an inert solvent may be diethyl ether or ether benzene mixture. Take an inert solvent such that solvent doesn't have any influence on the reaction. So in an inert solvent and followed by hydrolysis yields beta hydroxy ester. It yields beta hydroxy ester. Beta hydroxy, see, this is the alpha carbon atom, this is the beta carbon atom. This is the carbonyl group, right? So this is the alpha carbon atom, this is beta carbon atom. Beta hydroxy ester. Fine. So let us rewind what we have seen. A carbonyl compound, when it is heated with alpha halogenated ester in the presence of zinc in an inert solvent like diethyl ether, followed by hydrolysis, yields beta hydroxy ester. Beta hydroxy ester. I hope I am clear. Carbonyl compound, when it is heated with alpha halogenated ester in presence of zinc in an inert solvent such as diethyl ether, followed by hydrolysis, yields a beta hydroxy ester. Now the second point regarding this reaction is that Reformatsky reaction is a condensation reaction. It is a condensation reaction. Condensation reactions are reactions in which reactants add among themselves, they add to form an adduct with the elimination of a small molecule. The small molecule eliminated may be water, it may be methanol, ethanol, acetic acid. In this case, the small molecule that is eliminated is ZnBrOH. Okay, so this is a small molecule that is eliminated. The rest of the reactants are getting added. That is, here in this case, ketone and alpha halogenated ester, they are getting added to bring an adduct. The adduct is beta hydroxy ester, and what is coming out? It is a small molecule. So that is why Reformatsky reaction is a condensation reaction. It is a condensation reaction. Now let us understand the mechanism of the reaction. So the mechanism is nucleophilic addition reaction. Carbonyl compounds show nucleophilic addition reaction, be it aldehyde, ketone or ester, they show nucleophilic addition reaction. So the mechanism is nucleophilic addition reaction. It has got three steps. Step number one, oxidative addition of zinc, oxidative addition of zinc to carbon halogen bond, oxidative addition of zinc to carbon halogen bond. Okay, so let us see what happens and then I will explain the reaction. So this is our alpha halogenated ester, right? This is alpha halogenated ester. I'm going to apply some heat and zinc in the presence of zinc dust. Let's see what happens now. So Br Zn plus CH2 minus and COO C2H5. So this can rearrange like this. CH2 double bond C double bond ZnBr O C2H5. Let us understand what we have written here. So this is our alpha halogenated ester. This is the alpha carbon atom, alpha halogenated ester, right? This is an ester, right? So alpha halogenated ester. We are heating it with zinc. When we are applying this heat, okay, what happens? Two things happen simultaneously. One, Br and C bond, this one, Br and CH2 bond, it breaks, okay. And second thing that happens is zinc electron, it goes to higher states. From ground state it goes to higher states. Now zinc is electropositive. All metals emit electron, they try to give electron. So zinc, it is a it oxidizes, okay, it oxidizes bromine. What is the meaning of oxidation? Oxidation is loss of electron. So loss of electron, loss of one electron. How many electron deficient is bromine to reach its octet configuration? How many? This is the bromine. How many electrons are deficient? One more electron, right? So this one electron, that one electron is given by zinc, okay. So now what happens? Zinc gives one electron to bromine, okay. In that process zinc become positive. I have written that here. When zinc gives one electron to bromine, zinc become positive, correct. Now this electron pair, when bromine broke from carbon, when halogen broke from the carbon, the electron pair was left with the carbon. Now zinc is positively charged because it has lost its one electron to bromine. So it forms a bond with the carbon. It forms a bond with, it forms a bond with carbon like this. But the issue with this bond is that it is a very highly polar bond. Why? Because there is a significant amount of electronegativity difference between carbon and zinc. Carbon electronegativity is 2.5 while zinc's electronegativity is 1.25. So there is significant electronegativity difference between carbon and zinc. Yes, so it is electropositive. I agree, carbon is electropositive. Zinc is also electropositive, but zinc is highly electropositive, okay. With the result, carbon acts as relatively carbon is electronegative in nature. So what happens? A negative charge develops on this carbon and a positive charge develops on this zinc. So it's a very highly polar bond here, highly polar, and it is liable to break anytime. At the slightest provocation, this bond will break among them. So this is zinc carbon enolate. This is zinc carbon enolate complex. Zinc carbon enolate complex. Why enolate? See, this is the enolate, right? This is in enolate form. So this is zinc carbon enolate complex, okay. So now a better, as I said, at the slightest provocation it would break, correct. Now look at the carbonyl group here. Carbon and oxygen are of opposite nature. This is highly electronegative, correct, and this is electropositive. So ultimately what would happen? The electron would go to this side, oxygen side, correct. Here also there is an issue, okay, it is highly electronegative. This is electropositive. So ultimately what would happen? The electron would go to this side, correct. So zinc Br will dissociate from here and it can come and combine with oxygen, right? Because oxygen has got a negative charge, so it can combine with oxygen, right? And this pair of electron which it has left, it can come here and form a double bond. This is oxygen zinc enolate. Oxygen zinc enolate. They can interconvert among themselves. They can interconvert among themselves. So this is the first step. The first step is the most important step. So what we have discussed here is very let me write it once again, what I have discussed here. This is your alpha halogenated ester. When I am heating it, two things are happening at the same time. One, bromine and carbon bond is getting dissociated. Second, this heat is responsible for the electron to go into higher state. In zinc, the electron goes into higher state for zinc. At the same time, this is also getting dissociated. Now the electron of the zinc, because it has gone to higher state, it is available for donation. Okay, so zinc loses an electron. So when zinc loses electron to bromine, okay, so bromine, zinc loses electron to bromine. So zinc become positive. When bromine got dissociated, it left the pair of electron here. Okay. Now what can happen? Now they can form a bond, correct? But when they form a bond, what would happen? There is a significant electronegativity difference. So this side becomes negative and this side becomes positive. That is, it is a highly polar bond and it can break at the slightest provocation. So this is a complex. Which complex is this? Zinc carbon enolate. This is called as the zinc carbon enolate. From this, another thing it can reconvert. This exists as like this. Let me write like this, correct? So this is the zinc carbon enolate. It can reconvert to oxygen zinc enolate. How? See, look, here also there is a significant polarity difference. So ultimately electron will go to oxygen. Here also there is significant electronegativity difference. So ultimately electron will go to CH2, correct? And zinc Br will get positive sign. Now they can go and attach here. Now what could happen? It can become ZnBr. Fine. This electron, it can come here and form the double bond. So now what we got is, what is it? Oxygen zinc enolate. So both your carbon zinc enolate and oxygen zinc enolate, they can both coexist. They both are there. They are interconvertible in the first step. Both are existing. Okay, carbon zinc enolate is also existing and some of it is converted into oxygen zinc enolate. So this interconversion takes place in the first step. Now in the second step, both can enter. This can also enter and this can also enter. And first we will show how carbon zinc enolate enters the second step, and then we will show how oxygen zinc enolate enters the second step. Okay, so let us now go for step number 2. Step number 2. Step 2, nucleophilic addition. Nucleophilic addition, this is the main step. Nucleophilic addition of zinc salt of ester, both are zinc salt of esters only, with carbonyl carbon. Carbonyl carbon. Carbonyl carbon can be of ketone, aldehyde or any other ester. Here we have taken acetone as an example, which is a ketone. So let us see. So here this is our carbonyl carbon. So this is the carbonyl carbon. This is acetone, correct? This is a ketone. Now let us react it with the product of the first step. First we will write the carbon zinc enolate that we got What is it? ZnBr CH2 COO C2H5. It can react with this. In some book it is written like this, only with carbon zinc enolate. In some other books it is shown with carbon oxygen enolate. You can write any one of them. Both of them is not required. Writing both of them is not required. Any one of them you can choose. So in some books carbon zinc enolate has been demonstrated. So I am going to demonstrate that first. So this is the first, this is the second this thing. Now look at this. This side is positive, this side is negative. As I said, in the slightest provocation it can break. Look at this ketone molecule. There is significant electronegativity difference between carbon and oxygen. This side is negative, this side is positive. So there is polarity developed, and electron subsequently will be taken up by oxygen. Correct? Now the ZnBr part, it can come and attack here. When ZnBr part, when it comes and attack here, the pair of electron is left here. This is adding nucleophilically to carbonyl carbon, which is positive. Okay, the ZnBn part, the zinc Br, ZnBr, it prefers oxygen because oxygen is more electronegative. Let me tell you before learning this, that zinc will go to more electronegative atom. Relatively, which is more electronegative, there only zinc will go. Why? Because zinc is electropositive in nature. It wants to donate its electron. That is the tendency of the zinc. And the nature of zinc is to go to relatively more electronegativity, negative atom. More than carbon, oxygen is electronegative. So zinc Br will go to oxygen. Okay, when it goes to oxygen, it leaves its pair of electron here. So therefore that results in a carbon anion. This carbon anion is added nucleophilically to the nucleophilic carbon center, which is the carbonyl carbon. So now what we get is CH3, see, look at this, COZnBr, right? CH2, just add this, COO C2H5. Fine? Yes. This is with zinc carbon enolate. I have shown this with zinc carbon enolate. What happened? Zinc has a character of going to more electronegativity atom. Compared to carbon, oxygen is more electronegative. So zinc will go to oxygen. When zinc goes to oxygen and becomes OZnBr, this side becomes positive. When zinc goes, it leaves the electron pair here. With the result, the carbon anion now goes to nucleophilic carbonyl carbon, resulting in this product. I hope it is clear. Zinc, I have told you earlier, it's the character of zinc. Zinc is highly electropositive. So it's the character of zinc to come to a more highly electronegative atom. Okay, here oxygen is more electronegative. It can much more accept zinc than carbon. Okay. Now let me demonstrate this by using oxygen zinc enolate. Okay, from the first step. The same thing I am going to demonstrate with oxygen zinc enolate, and reason you out why ZnBr goes to oxygen. So this is our acetone, right? Let's use the second interconverted product, oxygen zinc enolate. What is it? CH2 double bond C OZnBr COO C2H5. That is the interconverted product, right? From the first step I said no, that both can exist. Either it can exist as carbon zinc enolate or it can exist as oxygen zinc enolate. So in some books you will find like this. Now what happens if this is what is reacting with acetone? What can happen? As I said, there is a rift between carbon and oxygen. Oxygen is electronegative, carbon is electropositive. That leads to a polarity. So this is a very polar bond, very polar bond. Now what happens? Oxygen here, it is more electronegative than oxygen here. Why? Because there are pumping groups, two CH3 groups. They pump their electron to oxygen. So the oxygen here receives much more, it's more having more electron density than this oxygen. Therefore zinc finds it easy, finds it more acceptable to move here. Okay, now let us draw here. So this goes here. When this goes here, what happens? Electron come here. When electron come here, ZnBr, it will move here. Correct? So now CH3, CH3, CO, ZnBr. When O become negative, carbon becomes positive. Correct? When this moved here, this electron pair, it went. When this moved here to this oxygen, there is an electron pair that was left here. That comes down to form double bond with carbon. When it comes down to form double bond with this carbon, this double bond, it comes back here, and that results in negative sign here. That results in a carbon anion. That carbon anion can now attach to positively charged carbonyl carbon. So that results in this structure. Correct? Both are same. Sorry, pardon me. This is OC2H5. Both are same, right? Yes, both are same only. This is also, pardon me, OC2H5. Correct. Both are same products only. What happened here is acetone, there is a rift between carbon and oxygen. Oxygen is electronegative, carbon is electropositive. Oxygen wins the game, it gets negative charge. This is having more electron than this oxygen. Why? Because there are two pumping groups. So ZnBr, it changes its side, it comes to this oxygen. When ZnBr comes to this oxygen, here it leaves a electron pair. That electron pair, it comes down and forms double bond with carbon. When it forms the double bond with carbon, this double bond, it comes here and becomes an electron pair. Now we got a carbon anion. This carbon anion, it can come and attack the nucleophilic carbon, which is a positive charge, which has a positive charge. So here also we are seeing the nucleophilic addition of the enolate ester. Correct? Nucleophilic addition of zinc enolate to nucleophilic carbon of the carbonyl compound. So we can get a product like this. So whether it doesn't matter whether it is reacting with your oxygen zinc enolate or it is reacting with carbon zinc enolate, which we have shown earlier. The end product is the same. Correct? In some books you will find this oxygen zinc enolate. In other books you can find carbon zinc enolate. You can find both. Now let us go for step number 3. Step number 3, hydrolysis. Step 3, hydrolysis. Hydrolysis. Okay. So now we are going for hydrolysis. This is subjected to hydrolysis. I am going to write this here. Acidic hydrolysis we are going to carry out. So that would make the reaction a condensation reaction. So this is what we got from second step. So now let us go for hydrolysis. Fine. Now what would happen? Hydrolysis will yield what? Yes, correct. Your product. So this is the product. The Zn, it would come like this. ZnBrOH. Elimination of a simple molecule and formation of adduct. That makes it a condensation reaction. So what happened here? Here H plus was we conducted acidic hydrolysis, right? In acidic hydrolysis, what happens when we are putting H plus here? There is a two lone pair of electron, right? So one of the lone pair of electron is taken by H. So that would make the oxygen positive, right? To remove this positive charge, oxygen says goodbye to ZnBr, right? ZnBr goes away. Now actually this is carried out in H2O. So it is aqueous hydrolysis. So it becomes H3O plus. One H plus has reacted here. There is one OH minus also. H3O plus is made up of H plus and OH minus. Right. So what happens when there is OH minus also? So that OH minus, it can come here and become ZnBr OH. When ZnBr goes from here, the positive sign also goes, and this one results. Right, that is what happens in acidic hydrolysis. So I hope you understand that we are doing acidic hydrolysis. Acidic hydrolysis means H. This is the acidic hydrolysis. So we are putting H. When we are putting H, what will happen? The lone pair of electron will be taken. When it is taken, oxygen become positive. To remove this positive sign, ZnBr goes. When ZnBr goes, this positive sign is gone. H comes here and takes the electron pair. The lone pair of electron is restored. This ZnBr now combines with OH to become ZnBr OH. So that results, the hydrolysis, that would result in what? This is the alpha carbon. This is the beta carbon. So what is it? Beta hydroxy ester. Beta hydroxy ester. So there we got our product, beta hydroxy ester. So that is a 3-step reaction. In second step, you can use either one. Either you can demonstrate carbon zinc enolate, or you can show the reaction with oxygen zinc enolate. No need to show both of the reaction. I have demonstrated both and I have shown the reasoning just to make you understand. Okay, in some books, so that you may not get confused, because in some books it is written zinc enolate, carbon zinc. In other books it is written oxygen zinc enolate. So both are correct only. So that is our product, a beta hydroxy ester. Now let us understand the significance of this. See, from beta hydroxy ester, if you are conducting hydrolysis, acidic hydrolysis, what can result? What can result? See, if you are going for hydrolysis, what will you get if you are hydrolyzing an ester? Yes, you will get an acid. So you will get this kind of acid here. So we get this kind of acid here, COOH. We get an acid. What is this acid? Alpha beta. What is it? Beta hydroxy acid. So you can make beta hydroxy acid out of beta hydroxy ester. Beta hydroxy ester can be made using Reformatsky reaction. So by Reformatsky reaction, you can make, indirectly you can make a beta hydroxy ester. A beta hydroxy ester. Okay. Now if you get a beta hydroxy ester, you can make one more thing. If you are going for a dehydrating agent like conc H2SO4 or HNO3, conc HNO3, if you are using a dehydrating agent, what will you get? OH will go from here, H will go from here. Okay, so you will get something like this. Yes, you will get this. What is this? Alpha beta unsaturated acid. What is it? Alpha beta unsaturated acid. So you can prepare alpha beta unsaturated acid. You can prepare beta hydroxy acid. Indirectly you can prepare them using Reformatsky reaction. Let us learn other significance of Reformatsky reaction. Number one is, other significance is you can prepare vitamin A using Reformatsky reaction. Starting product is beta inon. Beta inon. From beta inon, by doing Reformatsky reaction, you can prepare vitamin A. Vitamin A, you know, there is no doubt, it is used as a supplement especially in cases of dim vision, xerophthalmia. It is used as a nutraceutical in improving immunity and giving good skin health. So vitamin A, the precursor of it is beta inon, and we are converting this into vitamin A using Reformatsky reaction, and there are other steps also. So one of the step is Reformatsky reaction. Number 2, you can prepare your estrone. Okay, you can prepare estrone. It's also called as oestrone. Now estrone is a component of estradiol, is a component of estrogen. So estrogen has actually 3 subcomponents. One is estradiol, estratriol and estrone. Estrone is the most mildest among all. It's the mildest female hormone. So it is given as injection in postmenopausal women. In postmenopausal women, you are giving it as estrone. Also, you can convert it into estradiol through chemical reaction, which is more potent. Okay, so you can prepare estrone using this reaction. Number 3 is you can prepare citral. You can prepare citral. Citral is a terpenoid. It's a terpene, and you can prepare citral and limonene, and all other terpenoids you can prepare using Reformatsky reaction. Terpenoids are having ester groups. Okay, so citral, it has a lemon flavor and lemon odor, strong lemon odor is there, strong lemon flavor is there. So you can use it in perfumery, and you are also using it in food items. It has also got antibacterial, antifungal properties. That makes it a very successful preservative. So you can use citral in for its strong lemon odor and lemon flavor, and also you can use it as a preservative. Limonene also is a terpenoid. It also is used in perfumery in giving flavors. You can make any other terpenoids using this reaction, using Reformatsky reaction. Terpenoids are known for your flavor and odor. Some of the terpenoids are also useful as pharmaceutical agents. For example, curcumin. Curcumin is a pharmaceutical agent. Okay, it has got anti-inflammatory property and anti-cancer property. So all of these compounds, especially natural products, they can be synthesized chemically using Reformatsky reaction, and that makes Reformatsky reaction really a very significant reaction in organic chemistry. Dear students, I hope you have understood and I hope you have liked the class. If you have done so, please do not forget to subscribe the channel, do share it and do like it. Thank you very much.